All right, this first section I'm going to do is the measurements and the science skills. So remember, under measurements, we did rules of measurement, and with the digital measurement tool, we just recorded exactly what we saw. So this one would be 261.3, and the unit is grams. But then when we did the analog, we had to look at the measuring device and look at what each line was delineated to be. So here I can see it started at 0 and the next numbered thing is 10. And so each one of these line increments is 1. And so if I count over, I am sure that there is 3 kilopascals. And then I have to go one decimal beyond what I'm certain of. And if I look, the needle's a little past the 3, so I'm going to say 3.4, and it would be kilopascals. Okay. If I said 3.5 or 3.6, that would be fine. Coming over to the balance over here, I can see I have 100, 200. This one here is a 50. And so each one of these little lines is going by 10. And so I'm certain of 300. I'm certain of 310, 320, 330. And then I have to go one decimal beyond, which would be the ones place. So in this case, I would say 335 grams, 336, 334. Any of those would work. Coming to the graduated cylinder, remember that we read from the bottom of the meniscus. And if I look at the meniscus, it seems like it's right on this line right here, which would be the 90. Again, looking at the measuring device, each one of these increments is 1. So I have to go one decimal beyond the ones place to the tenths place. So if I'm looking at the bottom of the meniscus here, it looks like it goes right to the 90. So I'm going to say 90, and then I have to put 0.0 because that is the tenths place that I need to go to, and then this would be in milliliters. Coming to the ruler over here, if I look, I have my numbers are to the whole number. Each one of these increments then is to the tenths place, and I need to go one decimal beyond. So I'm certain that it's 7, and then point. It doesn't quite make it to the tenths place, so zero point 0, and then I need to estimate my next number, so maybe 7 centimeters. 7.06, 7.05 would all be fine. Okay, so that's it for the measuring devices. Always go one decimal beyond what you're certain of. So under science skills, we're going to look at experimental design. So when I come over here, I'm going to first read this experiment. A study was done to find if different tire treads affect the braking distance of a car. So right there, I know what I'm testing right now, what the independent variable is. The independent variable is going to be my tire treads. Tire treads are letter D right here. And then how they affect the braking distance. The braking distance is going to be my dependent variable that I'll be measuring. So then there's the control, that which you're going to compare to, and then constants, the things that you're going to keep the same. So as I read through, 4 different tire treads were compared to the stock tires. Okay, so they were compared to the stock tires. So the stock tires, letter E, is going to be your control. Okay, that's how you're going to know whether or not these different tire treads are good or not. And then the things that are going to be kept constant. So the tires were all the same size, tested on a 2018 Corvette. The Corvette was brought up to 70 miles per hour, and the brakes were engaged in the same way. So all of those are constants. So A, tire size, the 2018 Corvette, and then the 70 miles per hour is another constant, but I only asked for 2, but all 3 of those are your constants. Okay. So then we come down to this next one. In the future, you're given the opportunity to buy a chunk of gold at half the price of what it's worth. The chunk in question is shown below. So sensing a scam, you devise a plan to assume that the gold is in fact gold and not pyrite. So then you have these three techniques that you're going to look at. Technique 1, Technique 2, and Technique 3. And so this is the hunk down here of the gold or the pyrite. So let's look at Technique 1 here first. Using a small ruler, you measure the length, the width, and the height. Okay, we got a problem right there, because if I look at that hunk of gold, that is irregularly shaped, and I can't just take a ruler and measure the length, width, and height of that. So that's not going to work. Because you're assuming it's approximately cube-like in shape, but it's definitely not. And so this is going to just not work out for you. And then you're going to find the mass. If it was a perfect rectangular shape, then you could use this method. But the fact that it is irregularly shaped is going to negate this as one thing that you can do. So technique 2, using a large beaker. We talked early on that beakers should not be used for determining volumes. They are very imprecise. The delineations are by 50 milliliters. And we need to be a lot more precise than that. So I can tell you right now, without going any further than looking at beaker, that is not going to be a good way to do it. So then we look at the last one, using a large enough graduated cylinder. That is a good measuring tool. You're going to fill it partway with water and record the volume. Then you're going to place the chunk of water in and record the new volume. So here was your original volume. Here's your new volume. And the amount that it went up is your volume of the chunk. That is a good way of determining the volume. And then the mass is going to be found by placing the chunk on an electronic balance within 0.01 grams. And then use mass divided by volume. And so that is a great way of doing it. And so if I look at my data here at the bottom, it says the mass is 107.89 grams. So 107.89 grams is my mass, and then my volume. So I'm going to look over here, and I kind of wrote all over this, but let's say that this one was 20.0, and this one is 40.0. It's hard to see right now. But the volume then would be the difference between the two, which would be 20.0. And then all I would do is take my calculator, which I will grab right now, and divide 107.89 divided by 20.0, and I would get 5.395 grams per milliliter. And that is a density very similar to what you would get for pyrite and nowhere near what you would get for gold. So unfortunately, you're going to pay a lot for the pyrite, and that's not what you want to do. So then I come over here to our metric conversions. And so hopefully we remember how to do this. You will be given this table on the quiz or the test, sorry. And so I'm going to start off with 31.8 milligrams. The little m right there is milli right here, and that means 10 to the negative 3. And I'm going to go to centigrams, and centi is right here, and it means 10 to the negative 2. And so as I go from milligrams to centigrams, I am going from a smaller to a bigger unit. And so I'm going to move my decimal to the left. And the number of times I will move it is the difference between negative 3 and negative 2, which is 1. So I'm going to move my decimal one time to the left, and I'm going to get 3.18. For the next one, I have kilograms. Kilo means 10 to the 3, and milli means 10 to the negative 3. Okay. And so when I move my my decimal, I'm going to move it the difference between 3 and -3, which is 6 times. And because kilo is a bigger unit, so kilo is right here, and milli again is down here. So as I go from a big unit to a small unit, I'm going to move my decimal to the right 6 times. And so I'm going to get 96,000 milligrams. Okay. For the next one, I have 45.9 meters. That is my base unit. That's right here. That is 10 to the 0. And I'm going to go to centi, which we already looked at, which is 10 to the -2. So again, I'm going from my base unit down to centi. So I'm going to move from a bigger to a smaller unit. So again, I'm going to move to the right, and I'm going to move it 2 times. So I'm going to get 4590. For the next one, this symbol right here means micro, and micro is 10 to the -6. And I'm going to go to liters, which is my base unit, which is 10 to the 0. And so again, I'm going to change my color here. I'm going from micro up to my base unit. So I'm going from a smaller to a bigger, which means I'm going to move my decimal to the left. And when I do so, I'm going to move it 6 times. The decimal's not written. If it's not written, it's always in the back. And so I'm going to move it 3, 6. So I'm going to have 9.800756 liters. For the next one, I have giga. Giga is a very big unit. It is right up here, and giga means 10 to the 9. And I'm going to go to milli, which is a small unit. Milli is down here, and you'll recall it's 10 to the -3. So when I move my decimal, I'm going to move it 12 times. Okay, that's the difference between those two numbers. And because giga is a bigger unit than the smaller unit, I'm going to move to the right. And so I'm going to have 7, 8. That's moving it 1 time. And then I'm going to add 11 zeros. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so that is a very big number. Okay. And then my last one, this is a trick question right here. We have to recall that milliliters are equivalent to centimeters cubed. So because it's the same unit, just written differently, I just rewrite my number, 98.97. Okay. And that's all we do for those conversions. So then we come to scientific notation. Scientific notation, you always are going to have the times 10, and then the exponent is going to tell you if it's a big number or a small number. If it's a positive exponent, it's a big number. And the number tells you how many times you move your decimal. Because I have a positive exponent, I'm going to move my decimal in that direction to the right to make that a big number. And so I'm going to have 6, and then 7, 8. I've moved my decimal twice so far, and so I have to move 5 more times. So I'm going to have 5 zeros, 3, 4, 5, and here is my number. For this one, the -6 is a small, or a negative exponent means a small number. So I'm going to move my decimal that way 6 times. So I'm going to have 0 point, and then it's a nice, easy thing to remember. Your number of zeros to follow the decimal point is always going to be 1 less than the number of your exponent. So I'm going to have 5 zeros. 1, 2, 3, 4, 5, and then my 8, 9, 7. And the reason it's always 1 less is you had to move it 1 time to get it from behind whatever your first number is. And then the rest of them will be zeros. For the next one, I'm going to put it in scientific notation. So I'm looking at all my non-zero numbers, and I'm going to write my first number, 3, followed by a decimal point, followed by the rest of the non-zero numbers. And then I do my times 10. And then this is a big number. So my exponent will be positive. And then how many times did I have to move my decimal? Well, the decimal, if it's not written, it's in the back. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So I'm going to have 3.48 times 10 to the 10th. Okay. For the next one, again, looking at my non-zero numbers. So I write my first non-zero number, 8, followed by my decimal, followed by my 9-4, and then I do my times 10. This is a small number, so I'm going to have a negative exponent. And then how many times did I move my decimal? I started there, so I moved it 1, 2, 3, 4 times, and that's where I get that right there. All right, so now we're moving on to apparent size. And remember, you'll be given these two formulas. So here's our first formula, and then here is our second formula. And we just have to figure out when to use each one, which we'll look at here in a second. But first, as the distance of an object increases, the object's apparent size decreases. It does the opposite, okay? So the farther something is, the smaller it appears. And as the actual size of an object increases, the object's apparent size will also increase. Bigger objects look bigger, increases. Okay. For the next question, the moon is moving around a planet in an elliptical orbit. So the moon has an apparent size of 2 centimeters when at its farthest point from the planet. If it has an apparent size of 3 centimeters at a later point, what happened to the moon? Well, the moon didn't change size, but it did get closer to you. So, and we know that because it appears bigger. Why does it appear bigger? Because it's closer to you. And you're kind of given that hint when it tells you that it was at its farthest point. So obviously it will be getting closer as it orbits throughout its orbit. For the next one here, it's going to be a supermoon. You look at it and it has an apparent size of 2 centimeters. The moon is 220,000 miles from Earth. The actual size of the moon is 2,158.8 miles. And then it's asking, what is your sighting distance? So the only formula that has sighting distance in it is this one right here, and that is the formula that we'll be looking at. You are given the other three quantities. So we will start off apparent size. Our apparent size was 2 centimeters over sighting distance, which I don't know that, that's what I'm looking for, is equal to the actual size, which we have right here at 2158, that's terrible writing, sorry, 0.8 miles over the actual distance, which was 220,000 miles. Okay, we should right away see that we have miles over miles, so they're going to cancel out. My answer will be in centimeters. Sorry about that. My answer will be in centimeters, and I am going to cross multiply here. So 2 centimeters times 220,000 is going to give me 440,000 centimeters is equal to, and then I'll multiply these together, 2158.8 times SD. So then I just need to divide both sides by 2158.8. And when I do that, 2158.8, that will cancel out there, and I'll have 440,000 divided by 2158.8 equals 203.8. 203.8, and again, my answer was in centimeters. Okay, so that's how I do that one. I'm gonna clear this writing because I can't see the next one. And then so for the next one, an asteroid has an apparent size of 0.0003 centimeters when it is 50,000 kilometers from Earth. 48 hours later, the same asteroid has an apparent size of 0.0001 centimeters, and it wants to know how far. So to figure out which formula to use for this one, I don't see anything about sighting distance, and I'm given two apparent sizes and a distance here, and it wants a distance here. So hopefully we can see that that's going to be this formula right here. What I underlined in purple goes together, and what I underlined in green goes together. So it doesn't matter which one I call S1 and D1 and S2 and D2, as long as I keep those colors together. So I came across the apparent size of 0.0003 first. So I'm going to start there. So I'm going to have 0.0003 centimeters times 50,000 kilometers. So that's this part right here. And then equals, and then I'm going to have 0.0001 centimeters times, and this is going to be D2. Okay. So quick little sidebar here. I can conceptually understand what's going to happen here. It was 0.0003, and now it's 0.0001. It got smaller. Why did it get smaller? Because it got farther away. And it should be 3 times farther away because it's 3 times smaller. But we're going to see if this works out by doing the math here. So I'm going to divide both sides by 0.0001 centimeters. That's going to cancel that out. And over here, divide by 0.0001 centimeters. And I'll see that here, my centimeters cancel out, and I'm going to have 50,000 times 0.0003 equals 15, and then I divide that by 0.0001, and I'm going to get 150,000. 150,000, and my answer is in kilometers. And I see that indeed it is 3 times more than that number, and so I know that I did it right. Okay. So then I come down over here to parallax, and so remember, parallax is this symbol right here. It's that angle theta, and then r is the distance in parsecs. Okay, and I give you that information right over here. And then we can rewrite the formula as you see it here, that the parallax angle is equal to 1 divided by the distance. And then so stellar parallax is caused by the revolution or orbit of Earth around the sun, because we're orbiting the sun, and provides evidence for, this is called the heliocentric solar system, or a sun-centered solar system. Stellar parallax can be used to determine the distance of relatively close stars. A star that has a parallax of 1 second is 1 parsec away, and a parsec is 3.26 light years. Stellar parallax has an inverse relationship with distance, which means that as the distance increases, the parallax decreases to almost 0 for really far stars. Okay, actually, it's always going to have some amount of parallax, but it's going to get really, really small. Okay, so over here, parallax is 0.024 arc seconds. How far away is it? That's going to be our formula, r equals 1 divided by theta, and I'm just going to do 1 divided by the 0.024. And so 1 divided by 0.024 is going to give me 41.67. And again, that answer is in parsecs. Okay. For the next one, I'm telling you the distance, 147 parsecs, and it's asking what is the parallax. So the formula looks a lot similar. It's parallax equals 1 divided by r this time, and so 1 divided by 147. And if I do 1 divided by 147, I get 0.0068. and that would be arc seconds. Okay. A star has a parallax of 0.001 arc seconds. How far? So again, R equals 1 divided by theta, 1 divided by 0.001, and that's going to give you 1,000 parsecs. Okay. And then for the last one, hold on here. Excuse me. A star is 28 parsecs from the Earth. What is the parallax? Again, parallax equals 1 divided by the distance. So 1 divided by 28. And if you do 1 divided by 28, you get 0.0357. So I'm going to round off to 0.036. And that would be arc seconds. All right, you're not going to need to do this on the exam, but I'm going to show it anyway because I had it here and I think I actually took it out of your stuff. But if you wanted to convert miles, parsecs to miles, you would do your 7.8 parsecs, and there are 3.26 parsecs per 1 light year. And then there are 5.88 times 10 to the 12th miles per 1 light year. And then you would simply multiply across and you would get about 1.5 times 10 to the 14th miles. But like I said, that's not going to be on the exam, but I had it on my old review guide, so I figured I'd show it. Okay. So coming over to Kepler, according to Kepler's first law, planets travel in elliptical orbits with the sun at one focus. Due to this, a planet is sometimes closer to the sun, which is called perihelion, than it is at aphelion when it is furthest away. His second law, in conjunction with Newton's law of gravity, explains why planets travel. I lost my train of thought. Planets travel slower when farther from the sun. Kepler's third law is mathematical and relates to the period of a planet. To its distance. And that's that p squared equals a cubed. That is right here. Okay, so that is his third law. His second law, again, is saying that when the planet is out here at aphelion, it travels slower than when it's right over here at perihelion, because there is more gravitational force acting on the planet. So coming down here, according to Kepler's third law, a planet that orbits a star like the sun at a distance of 13 AUs will have a period of, and so we're just going to use our p squared equals a cubed, and I'm giving you the distance of 13 AUs. That's the a right here, and so I'm going to have p squared equals 13 cubed, which is equal to 2197. That's p squared equals that number. So I need to take the square root of that number and the square root of p squared, and that will lead me to p equals, and I'll get 46.9 years. All right. For the next one, according to Kepler's third law, a comet that orbits a star like our sun with an orbital period of 145 years will be what distance from the sun? So for this one, I'm just going to rearrange what I have here. I'm looking for my distance, so I'm looking for the a, so a cubed equals, and instead of p squared, I'm going to write my 145, and I'm going to square that number, and if I square that number, I get 21,025. So that's a cubed equals that number. So in order to get just a, I'm going to take the cube root of both, and I'm going to get A equals, and that would be 27.6 AUs, or astronomical units. Okay. So then going down here, Newton's first law tells us that if planets were not subjected to an external force, they would travel in a straight line. And at a constant speed or velocity. Speed, really, because the straight line gives you the velocity. Newton's second law explains that the planets are constantly accelerating. In their orbit around the sun. Newton's third law explains that the force that the sun is exerting on a planet is equal to the force the planet is exerting on the sun, just in the opposite direction. Let's see. Newton's law of universal gravity shows that the gravitational force between any two bodies is directly proportional to the mass of the two bodies and inversely proportional to the square of the distance between them. This means that if the mass of one object is doubled, the gravitational force will be doubled. But if the distance between the two objects tripled, then you would get 1/9, 1/9, or 9 times less gravity between them. All right, so then over here, one object has a mass of 3,000 kilograms. Another object has a mass of 5,000 kilograms. Both objects are separated by 1,000 meters. If the first object's mass were doubled to 6,000 kilograms, what would happen to the force of gravity? So remember that force is proportional to mass. So if I double that, I double that. So it would double 2 times. If the mass of each object were returned to 3,000 kilograms and 5,000 kilograms, but the distance was increased to 4,000 meters, what would happen to the force of gravity? So now we're saying that the mass didn't change from the original. So now we're going to say the force is proportional to 1 over the distance squared. Okay, and the distance is now doubled, right? So I went from 2,000, or no, I'm sorry, the distance is quadrupled. I've returned to 3, but the distance was increased to 4,000 meters. It was 1,000 meters. So I'm going to have 1 over 4 squared is 1/16. So gravity will be 16 times weaker, or 1/16 of what it was. And then if the mass of the first object was doubled to 6,000 kilograms and the mass of the second object was quadrupled to 20,000 kilograms and the distance between the two objects was cut in half, what would the force of gravity be? So for this one, remember that F is proportional to M1 M2 over D squared. And so the first mass was doubled, so 2. The second mass was quadrupled, so 4. And the distance was cut in half, so I can do 1/2 or 0.5. And then don't forget, we got to square that number. So I'm going to have 8 over 0.5 squared is 0.25. So 8 divided by 0.25 is going to be 32. So gravity would be 32 times greater in that instance.